Has the mystery of the Hubble tension finally been solved? The fact that the universe is expanding faster in reality than it should in theory is one of the greatest mysteries in space research. But now experts from the universities of Bonn and St. Andrews have discovered something that could lead directly to the solution of this nagging astronomical problem. Our Milky Way may be located in a gigantic void and thus in a particularly empty area of the cosmos. And lo and behold, as soon as we apply an alternative theory of gravity, the discrepancy between the theoretical and actually measured expansion rate of the universe can be explained quite simply. Unfortunately, however, there is a tiny catch to this groundbreaking approach. It is in stark contradiction to the cosmological standard model. What has long been part of the basics of astronomy today marked no less than a profound paradigm shift about 100 years ago. For generations, researchers of the past were convinced that the cosmos was a rigid, unchanging construct. Even a certain Albert Einstein initially held on to the idea of a static universe to such an extent that he added a cosmological constant to his equations, a step he later regretted as the greatest folly of his life. And although the young Belgian priest and astrophysicist Georges Lemaitre had already shown Einstein in 1927 how a mathematical model describing an expanding universe could be developed from the general theory of relativity, Einstein dismissed this concept as a mere mathematical gimmick. In retrospect, however, we know that Lemaitre's findings had a decisive advantage. After all, they made a prediction that could actually be observed. Specifically, it bridged the gap between the expansion of the universe and the light from galaxies. If the universe is really expanding, the other galaxies in space should move away from us just as the dots drawn on a balloon move away from each other when it is blown up. In the same breath, the light from the galaxies would be stretched on its way to us, and the wavelength would be stretched, and the light that touches our earthly eye would ultimately be shifted into the red. And indeed, in the late 1920s, the American astronomer Edwin Hubble was able to prove just that. The laborious examination of dozens of galaxies at the Mount Wilson Observatory in California showed that the light was indeed redshifted, and the expansion of the universe was practically observable. However, this circumstance was also linked to a no less revolutionary reverse conclusion. If the universe is constantly expanding, then viewed in reverse, it must also have had an origin, a tiny point from which everything once emerged. And while that tiny point is now at the heart of the Big Bang Theory, in the 1990s astronomers realized that the cosmos is not only expanding, but that its rate of expansion is also increasing. Dark energy is thought to be the mysterious driving force behind this acceleration, an unfathomed force that is supposed to counteract the force of gravity. The mysterious Hubble tension. Why is the universe expanding faster than it should? A fundamental core of the cosmic expansion puzzle, however, consists of the question of how fast the universe is expanding in detail. On paper, the corresponding pace is indicated by the so-called Hubble constant, but in practice, the exact determination of this value has led experts into a field of confusing deviation collectively known as a Hubble tension. According to the standard model, the Hubble constant should be around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec is about 3.26 million light-years, while 1 light-year is 9.46 trillion kilometers. In other words, this means that the speed at which the galaxies in space move away from each other increases by 67 kilometers per second every 3.26 million light-years. That's an impressive 244,000 kilometers per hour per megaparsec, but it can be significantly faster. As already mentioned, these are only the theoretical predictions. But when we determine the value of the Hubble constant with direct astronomical measurements, using supernovae, gravitational lenses, variable stars, or red giants, it suddenly amounts to 73 kilometers per second per megaparsec. That is again 264,000 kilometers per hour per megaparsec, and thus a discrepancy of a whopping 20,000 kilometers per hour per megaparsec. But how can this significantly higher value be explained? Is it possible that past investigations were flawed with falsifying measurement errors? Well, this was precisely the question that the James Webb Telescope addressed when it scrutinized the data from the Hubble telescope in the course of new observations. Specifically, the research team led by Nobel Prize-winning physicist Adam Rees of Johns Hopkins University in Baltimore focused on the data that Webb had collected over the previous 2 years. Since the capabilities of the most modern space telescope of all time far exceed those of its scientific predecessors, experts say that it shows us the universe in HD, so to speak. And so the experts were able to enjoy a razor-sharp confirmation of the Hubble tension. The evaluation of the largest Webb dataset to date, which included supernovae, variable stars, red giants, and a class of carbon-rich giant stars, show that the cosmos does not actually behave as predicted by the theory. Accordingly, the overall result this time also yielded a Hubble constant of 72.6 kilometers per second per megaparsec, and according to Rees, the discrepancies between the predicted and observed expansion rates literally scream that our understanding of the universe is simply incomplete. In this regard, it's conceivable that we have so far overlooked a component that gave the young cosmos an unexpected impulse after the Big Bang. Furthermore, it could also be that dark energy is changing. For example, that it is denser or more intense today than in the earlier cosmic chapters. It should be noted at this point, however, that researchers are also discussing alternatives to the influence of dark energy, and one of these is based on the exciting idea that the Milky Way, along with our Earth, is located in a gigantic void. The supervoid is the Milky Way trapped in a supervoid. To understand what this gigantic void is all about, we first have to recall the overarching structure of the universe. As is well known, stars and planetary systems are found in galaxies, which in turn combine to form galaxy clusters and then form superclusters. For a long time, researchers saw the largest coherent structures in the universe in such superclusters. But then the large-scale surveys showed that the superclusters are by no means randomly distributed in space, but rather arranged in a network-like structure. The lattice of this structure is formed by long fibers known as filaments, which can be several hundred million light-years across. In the same breath, the filaments also span gigantic, virtually matter-free bubbles, the so-called voids. And although the nightly view of the firmament resembles an exuberant astronomical spectacle, some researchers assume that these cavities even make up the majority of the cosmos. Expressed in figures, this means that an estimated 50 to 90% of the universe is characterized by a yawning void of matter. And a study led by Sergei Myrov of the University of Bonn now suggests that the influence of the voids could even lead directly to the solution of the expansion riddle. The study, carried out in collaboration with scientists from the University of St. Andrews in Scotland, is based on a new observation showing that the Earth is actually located in a region of space with relatively little matter, much like an air bubble baked into a cake. Consequently, the density of matter around the bubble is much higher, and gravitational forces emanate from it, pulling the galaxies inside the bubble toward the edge of the cavity. And what sounds both simple and plausible could ultimately mean nothing more than that as a result, the galaxies are moving away from us faster than one would actually expect. In this context, the deviations of the Hubble constant can therefore be explained quite simply by a local underdensity. A simple explanation, but one that has a small but crucial catch. The standard model does not provide for such underdensities or voids at all. Since matter and space should actually be evenly distributed, they should not exist at all. But how then can the 600 million light-year distant galaxies be explained, for example, which were examined by another research group, and which are moving away from us 4 times faster than the standard model of cosmology allows? Well, in this regard, Pavel Krupa, who was also involved in the void study, states that the standard model is based on a theory of the nature of gravity proposed by Einstein, and that gravitational forces may behave differently than the creator of the theory of relativity expected. Specifically, the research groups of the universities of Bonn and St. Andrews use a modified theory of gravity in their computer simulation. The modified Newtonian dynamics, or MON for short, were proposed by the Israeli physicist Mordechai Milgram around 40 years ago and is still considered an outsider theory today. And yet MON predicts the existence of huge empty bubbles in space, and that is precisely the crucial point. Because if gravity actually behaves as Milgram assumes, the problem of the Hubble tension would disappear in one fell swoop. And since the observed deviations would be due to irregularities in the distribution of matter, there would indeed be only one constant for the expansion of a universe. Conversely, however, this would also mean that we would have to abandon the established theories of Newton and Einstein about the nature of gravity. And Krupa complains that this is precisely the formidable research hurdle. More specifically, the astrophysicist refers to the strong lobby of established theories, which has a significant influence on the allocation of research funds. Competing approaches that challenge long-established ideas are often dismissed out of hand as unscientific, which is why it's all the more difficult to obtain funding from the relevant committees. Our committee has just approved your free subscription. We'd be happy if you click the thumbs up and hit subscribe now, so you'll never miss a new video from us again. We'll see you soon.